Have you ever asked an AI, maybe something like ChatGPT, to whip up some code for you?
Oh, yeah, I think most people playing with these tools have.
And you get this script. Looks perfect, right?
Yeah.
Syntax clean, logic seems okay.
Uh-huh. It's totally legit.
Then you hit run, and nothing. Or worse, it crashes, it gives you weird results. It's pretty frustrating.
It really is. You spend time trying to figure out what went wrong with this seemingly perfect code.
Exactly. Well, today we're diving deep into something pretty huge, a breakthrough in AI code generation that might just fix that exact problem.
Yeah, this is genuinely exciting stuff. It's not just a small tweak. It feels like a fundamental shift.
So this is our mission for this deep dive. Really unpack what this means, how AI is moving past just like mimicking code to actually thinking like a coder.
Right. And exploring why this isn't just a victory for programmers, but maybe a key step for AI overall, how it opens up, a whole new chapter.
Okay, let's set the stage first.
Yeah.
Why was the old way so flaky? Why did AI code look good but fail so often?
Well, that's the core issue they've been tackling. These large language models, LLMs, they're amazing pattern matchers.
They see billions of lines of code, they learn the pattern.
Exactly. So they can generate code that looks grammatically perfect, syntactically sound, the structure is right, the keywords are there.
Yeah.
But it often didn't actually work. It would crash, hang, produce the wrong output. There was a disconnect between form and function.
So it was like, you mentioned in an analogy before, the actor.
Yeah, the actor memorizing a script in a foreign language. They can say the lines perfectly, sound totally convincing.
Fluent, even.
Absolutely fluent. But they don't understand the meaning behind the words. They couldn't improvise or answer questions about the content.
Okay, so the AI knew what code looked like, but not how it actually executed or what the result meant.
Precisely. It nailed the surface appearance, the syntax, the common structures it had seen. But the underlying executability, the actual computational steps and their consequences,
Yeah.
that was missing.
So it wasn't necessarily that the AIs weren't smart enough in terms of language processing.
Yeah.
It was the fundamental approach.
I think that's a fair assessment. The dominant method for years, used by pretty much everyone, even the big players like Google and OpenAI, was this generate then test approach.
Generate, then test. Okay, break that down.
Pretty much what it sounds like. You give the AI a prompt, say, write a Python function to sort a list.
Okay.
The AI would then generate the entire function, all the lines, the loops, the return statement, everything. One complete block of code.
Right, it spits out the whole thing.
Exactly. Only after generating that whole chunk would it then try to run it, maybe against some test cases.
Ah, I see. So the testing happens after the creation is totally finished.
Yes. And if it failed, if the code crashed or gave the wrong answer.
Well, then just try again.
Basically, yeah. Either try to debug that whole block, which is hard for an AI, or more commonly just scrap it and generate a completely new version, hoping it gets it right the next time.
That sounds incredibly inefficient, like building a whole car and only then checking if the engine starts.
That's a great analogy. Or the one we used before the chef.
Right, the 5-course meal chef.
Imagine that chef cooking everything soup, appetizer, main, dessert, start to finish, never tasting the soup for salt, never checking if the sauce is seasoned, never probing the steak.
Blindly following the recipe steps.
Blindly following the recipe. Only when everything's plated and on the table do they finally take a bite.
And if the soup's salty.
Too late. The whole meal prep was based on a hope, a guess that the recipe would work out perfectly without any checks along the way.
That really highlights the flaw.
Yeah.
The AI was essentially guessing based on patterns,
Yeah.
not confirming through actual execution as it went.
Spot on. It was pattern recognition taken to the extreme. It guessed what working code should look like based on its training data. It couldn't verify actual functionality step by step.
Which is completely different from how humans code, right?
Totally different. A human developer writes a few lines, maybe a function header and a loop.
Then you run it, maybe print some values, see if it's doing what you expect.
Exactly. It's this constant, tight feedback loop. Write a bit, test it, see the result, fix it or adjust, write the next bit. It's iterative.
And AI just couldn't do that iterative test-as-you-go process.
And not in this way, not with this kind of real-time execution feedback guiding the next line being written. Until now.
Okay, so the impossible is now possible. What is this breakthrough? How did they crack it?
This is where it gets really cool. Researchers developed a new method, and the core idea is enabling AIs to run code while they are writing it.
Run it while writing it, not after.
Exactly. The technique is called execution-guided classifier-free guidance, EGCFG for short.
EGCFG. Okay, sounds technical. What's the simple version?
Forget the name for a second. Think about the process. Instead of writing huge code blocks, the AI now works more like, say, a chess grandmaster, thinking ahead.
A chess grandmaster. How so?
A grandmaster doesn't just make a random move. They consider several possible moves, think, if I go here, they might go there. Evaluate the consequences of each potential move.
And then choose the best one based on that look ahead.
Precisely. EGCFG works in a similar, highly iterative way, but at the level of single lines of code.
Single lines. Wow. Okay, walk me through the steps.
No.
How does EGCFG actually build code?
Okay, it's roughly a 5-stage loop happening very quickly for each line. Stage 1, write a single line of code. Just one statement, often. Very small
Yeah,
increment.
tiny steps. Got it.
Stage 2, pause and think. Before writing the next actual line, the AI generates several possible next lines, like exploring different branches in a decision tree. What could logically come next?
So it brainstorms potential continuations.
Sort of, yeah. It generates a few candidate lines based on the code written so far. Then comes stage 3. Run a quick test.
Testing already. After just one line plus a candidate.
Yes, but it's a mini test. It takes the existing code, tacks on one of the candidate lines, and runs this incomplete snippet against test cases. It's like
Yeah.
a tiny virtual execution.
Virtual execution.
Yeah.
Okay. So it's simulating what would happen.
Exactly. It's not necessarily a full compile and run. It's a lightweight check using the test cases provided. Does adding this line immediately break something obvious? Does it move closer to the goal?
And what does it get out of that test? Just pass-fail.
No, much richer than that. Stage 4 is get instant feedback. The AI analyzes the result of that virtual run. It gets what they call an execution trace.
An execution trace, like a log file.
Kind of. It's a detailed record. Did it error out? If so, where? What were the
Yeah.
values of variables? Did it produce any partial output? It's granular feedback on the consequences of adding that candidate line.
Okay, so it sees exactly what happened, good or bad, for each potential next line.
Right, which leads directly to stage 5. Choose the best path. Based on those execution traces, the AI compares the outcomes. Candidate A caused an error. Candidate B produced output closer to the target.
Candidate C did nothing useful.
Exactly. It intelligently discards the bad paths and selects the candidate line that produced the most promising result according to the test cases.
And then it actually writes that chosen line.
Then it commits that line. And the whole cycle repeats for the next line. Write a line, pause, generate candidates, test candidates, get feedback, choose the best, commit, repeat.
Wow. That is fundamentally different.
Yeah.
It's not debugging after the fact, it's course correcting during creation.
That's the crucial distinction. It's a real-time, line-by-line feedback loop. The execution results from testing candidate line N directly inform the choice of which line N gets written, which then influences the candidates for line N plus 1.
It's like what the GPS analogy you mentioned. Not a static map, but a live system constantly checking traffic and rerouting.
Perfectly put. The old way was the printed map, a guess based on past data. EGCFG is the live GPS dynamic, real-time intelligence adapting based on current conditions, or in this case, actual execution feedback.
Okay, the concept is clicking now, but can we see it in action? Give me a concrete example. How does this AI thinking play out on a real problem? Make it less abstract.
Sure. Let's use an example from the research paper itself, a classic little coding puzzle. Write a Python function to find the first non-repeating character in a string.
Okay, like in ABC, the first non-repeating character is C, right? Because A repeats. B doesn't repeat, but C comes first among the non-repeaters if you read left to right properly.
Exactly. B appears only once, but C appears only once and is the first one you encounter that fits the bill when considering the whole string context. It's a bit tricky.
So how would the old generate then test AI likely mess this up?
The old AI, relying purely on patterns, might generate code that iterates through the string, counts character occurrences, and maybe returns the first character it finds with a count of 1.
Which in ABC would be...
It might incorrectly return B, because B is the first character it encounters during the iteration that has a count of 1. It wouldn't necessarily have the full context or logic to realize C is the correct answer, according to the problem definition.
And it would only find out it was wrong.
After writing the entire function and running the test case ABC, it would see the output B, compare it to the expected C, register failure, and then have to backtrack or regenerate blind alley.
Right. Trial and error on a large scale. Now paint the picture with EGCFG tackling ABC. How does this thought process differ?
Okay, so the EGCMG AI starts writing. Maybe it writes the function definition, sets up a frequency counter like a dictionary or hash map, standard stuff.
Define first non-repeating, that kind of thing.
Exactly. Then it gets to the core logic, maybe the loop where it iterates through the string to populate the counts, or perhaps a second loop where it checks for the non-repeating character. Let's say it's at a critical if statement inside that loop. It pauses.
Okay, pause point. What happens now?
Now it generates candidate next lines, or logical steps. Let's simplify and say it considers two main logical paths for what to do inside the loop checking for the first non-repeater. Candidate A, the simple check. If counts character equals 1, return character. Candidate B. Maybe something slightly different, perhaps incorporating positional information or delaying the return. Let's imagine, for simplicity, it's just a placeholder for a slightly more complex logic check that doesn't return immediately.
Candidate A looks plausible, right? Find count to 1, return it. That seems like the goal.
It does, and that's the beauty. The AI doesn't assume. It runs a quick virtual test. It takes the code written so far, appends candidate A, and runs it virtually with the input ABC.
And what does the execution trace show?
The trace for candidate A shows that when the loop hits B, counts to B is indeed 1, and this logic would immediately return B. The AI gets feedback. This path returns B for input ABC.
Which it knows, from the test case definition, is the wrong answer.
Correct. Failure signal for path A. Then it tests candidate B, the more complex logic. Let's say that trace shows it correctly identifies A as repeating, processes B, notes it's non-repeating so far, but crucially doesn't return immediately. It continues to C, finds it's also non-repeating, and eventually the logic correctly identifies C as the first one encountered.
So the feedback for path B is, this path leads towards the correct answer C.
Exactly. Success signal, or at least more promising path signal. So the AI gets this immediate, concrete feedback. Path A is flawed for this test case. Path B is better.
So it learns right there in that moment.
It learns instantly. It realizes, okay, simply checking count 1 isn't sufficient logic here. It leads to premature, incorrect returns. It discards path A, commits to path B, or refines it further based on the feedback, and proceeds to the next line, now armed with a deeper understanding gained from execution.
That is the shift. It's using the execution feedback to guide its reasoning, like a human debugging on the fly. It's not just parroting code patterns anymore.
That's exactly the moment. It transitions from parrot to problem solver. It starts to think using execution as its guide.
Mind-blowing. And you said this isn't just theory, it actually produced results. How good are we talking?
We are talking exceptionally good. The researchers tested EGCFG rigorously on standard coding benchmarks. These are like the Olympics for code-generating AIs. Tough challenges.
Did the new message just edge out the competition?
Edge out. It blew past them in many cases. And here's the kicker. They achieved these results using an open source model, DeepSeek v3, not some proprietary trillion-parameter behemoth locked away in a vault.
Wait, an open source model with this technique beat the big guys? That's huge news in itself.
It's massive. Let's look at the scores. On MBPP, mostly basic Python problems, EGCFG hit 96.6% accuracy.
96.6. That sounds incredibly high. How does that compare?
It surpassed nearly all other reported results, including those from models like GPT-4 and Claude 3.5 Sonnet on similar benchmarks. It's basically top of the class for these kinds of problems.
Wow. Okay, what about harder tests?
Good question. They tested it on human eval ET. The ET means extended tests, making it tougher with more edge cases. Here, EGCFG scored 87.2%.
And how does that stack up?
That set a new state-of-the-art SOTA record. The best score ever recorded on that benchmark. Full stop.
A new SOTA. Okay, this thing is consistently performing. Any other benchmarks?
Yes, one more key one. Code contests. This uses problems from actual competitive programming sites. It requires complex algorithms, real problem-solving skills.
The really tricky stuff.
Exactly. And here, EGCFG achieved 58.18% accuracy, which, again, set another new SOTA, significantly outperforming previous methods, including those based on GPT-4.
3 benchmarks, top-tier performance, multiple SOTAs using an open-source model. That's really something. I look at the bar graph from the research, and it's just dramatic. EGCFG, with its blue whale logo, is towering over Quality Flow from Google, LPW from OpenAI, CodeSim from DeepMind.
It really visualizes the leap, doesn't it? An open-source model available to everyone paired with this smarter execution-guided technique is now outperforming the closed-source giants.
It really drives home the point. This isn't just a small step forward.
No, this feels like a paradigm shift. It proves that the path forward for AI isn't just about scale, about making models bigger and bigger. It's about making them smarter in their fundamental approach. Better algorithms, better reasoning processes.
That has profound implications, not just for coding, but for AI development in general.
Yeah.
So let's broaden out. What are the wider impacts of this? Where does this take us?
Well, first, it could signal the end of the era of just plausible code.
Right.
Code that looks right but doesn't work. We're moving towards AI generating code you can actually trust more.
More reliable AI-generated code from the get-go.
Exactly. And that opens the door to more capable, autonomous AI agents. Imagine an AI that doesn't just write a function, but can be tasked with building an entire feature or a microservice.
From scratch.
Potentially,
Yeah.
building it, writing the tests, using maybe the same execution feedback loop, running the tests, deploying it to a test environment, maybe even monitoring it, all autonomously.
That really elevates the AI from a coding assistant to potentially a project executor.
It does. It shifts the human role further towards architecture requirements, oversight, and away from line-by-line implementation. But perhaps even more significant is the democratization aspect.
Because it was done with an open source model.
Yes, that's crucial. This powerful technique isn't locked behind a corporate firewall. DeepSeek v3 is open source. The EGCFG method is published research.
So anyone can use it. Researchers, startups, individual developers.
They can build on it, experiment with it, integrate it. It prevents this potentially transformative tech from being monopolized by just a few huge companies. It fosters wider innovation.
That levels the playing field significantly. Does this technique itself, this generate test guide loop, have potential beyond just coding? Could it be a blueprint for other kinds of AI reasoning?
I absolutely think so. Think about the core loop. Generate possibilities, test them against reality or simulation of it, use the feedback to guide the next step. Isn't that fundamental to how humans solve problems, how science works?
Hypothesis, experiment, analyze results, refine hypothesis. Yeah, it sounds very familiar.
Right. We've now successfully implemented a version of that loop in a machine for a complex, logical task. So why not apply it elsewhere?
Like scientific discovery, AI generating hypotheses, testing them virtually.
Or engineering design. AI designs a part, simulates its stress tolerance, identifies weak points from the simulation feedback, redesigns, repeats.
Medical diagnosis, proposing diagnoses, checking against patient data and known outcomes, refining the probability.
Exactly. The potential is vast. This generate test guide framework could be a fundamental building block for AIs that can tackle complex real-world problems across many domains, grounding their reasoning in actual or simulated outcomes.
It really feels like a cornerstone piece falling into place. For so long, AI has amazed us with language, with art, but there was always that nagging doubt about its grasp on hard logic and real-world consequences.
The plausibility gap. It could dream, but could it do reliably?
Right. And moving from just generating code to executing it line by line using that feedback, that feels like it anchors AI much more firmly in reality.
It's a profound step. We haven't just taught the machine the grammar of code. We're teaching it how to reason with code using execution as its teacher, from imitation to verifiable function.
That changes everything. It feels like the question isn't, can AI become a reliable programmer anymore? It's shifting to, how do we adapt when AI might become the best programmer in the world?
That's the big question, isn't it? And that really brings it to you listening to this. What's your take on all this? Does this feel like the most significant leap for AI and software development you've seen? And looking ahead, what part of this evolution excites you the most? Or maybe even makes you a bit nervous? What comes next?